Hi, welcome to Physics Teacher. In this video I'm going to go over the final problem in the grade 11 math Fermat contest from 2020. It's a challenging one, so give it a quick try and I'll be right back with the answer. Alright, so this question says that there are three real numbers, x, y, and z, that are chosen randomly, completely independent of each other. Now they do have a domain that's between 0 and 1. And the question is, what is the probability that both x minus y and x minus z will be greater than negative a half and less than positive a half? Alright, so let's do this. We're going to take a cube, each with dimension of 1, so length, width, and height are all equal to 1. That would mean that if we were to choose a coordinate or a point inside of that cube, whose coordinates would be x, y, and z, as shown here, and then we look at the conditions that are given in the question, where minus 1/2 must be less than x minus y, which is also less than positive a half, and minus 1/2 must be less than x minus z, which is less than positive a half, will show us which part of those cubes is actually inside of these restrictions. Therefore, the probability that a point randomly chosen inside of this cube that satisfies these conditions will be equal to the volume of that region defined by those conditions divided by the volume of the whole cube. Basically, where we would randomly pick a point inside of this region compared to anywhere in the cube. Now, since the volume of the cube has a total volume of 1, then this simply means that the probability of randomly picking a point inside of these conditions is simply the volume of the area inside of that cube enclosed by these conditions. So that's all we need to figure out. It sounds a little bit easier than it actually is, though. Alright, let's start with this first condition, the x minus y one. So we'll look at the xy plane then. Now if I multiply everything by -1 and add x throughout, I can rearrange this inequality to look like so. It will be x minus 1/2 must be less than y, which must be less than x plus 1/2. So if you look at it, this is an equation. What this is telling us is, if we look at the equation of the line y equals x minus 1/2, and we look at the equation of a line y equals x plus 1/2, then this condition is showing us that the region above this x minus 1/2 and the region below this x plus 1/2 is the region we're interested in. And it will look something like this. Now similarly, we can look at the xz plane for this second condition. And I can do the same thing to the domain to shift it to be x minus 1/2 must be less than z, which must be less than x plus 1/2. So what we're going to do now is split this cube here into 8 smaller cubes. And now I can use the conditions in our xy plane to essentially slice this cube using these restrictions for our xy plane. And it will look something like this. Now if we just look at one level or one slice of this cube, we can see that this cube, or this portion of this cube, and this one are fully enclosed by those restrictions. Whereas the other cubes here are only half enclosed by these restrictions. Now this red outline is what you would see in the xz plane, and that's going sort of into the screen there. So we have slices along the XY plane and slices along the XZ plane. And inside of this cube, we have split it into 8 smaller cubes, each with a dimension, length, width, or height equal to 1/2. And some of them are composed of the entire area that we're looking for, and some of them only have half the area that we're looking for. So what I want to do is make a chart to see which of these 8 cubes are sliced by which restriction. Let's number these 8 cubes. This will be number 1. It'll be the bottom front left. The bottom front right will be number 2. And the bottom back left, let's call that one 3, 4. At the bottom back right, and then the top front left, let's call that one 5. And then 6, 7, and 8. Now if we're looking at number 1, looking at the slice on our XY plane, it does not get sliced at all. So no, let's just write no. And if we're looking at number 1 again in our XZ plane, once again, no, it does not get sliced. And what about number 2? Number 2, if we're looking at the blue lines, yes, it gets sliced in half. So let's write a yes there. With number 1, number 2. Yes. And what about in our XZ plane? Yes, it gets sliced in half here as well. So yes. And let's keep doing this for all of our other cubes. Alright, so we have 2 cubes here and here, numbers 1 and 8, that are not sliced at all. If they're not sliced at all, their entire volume contributes to the volume of our enclosed area that we care about. And that volume would be 1/2 cubed, since their dimensions are 1/2 by 1/2 by 1/2, which is a total of 1/8. And we have 2 of these. So 2 goes times 2, which would be 2/8 or 1/4. Now we have 4 of them, which are sliced either by one or another, numbers 3, 4, 5, and 6. These are either sliced by the XY plane or the XZ plane. And so the cube gets sliced in half. So instead of having an area of 1/8, they would have an area of 1/16. And we have 4 of these half cubes, which gives us a total area of 4/16, or 1/4. Now finally, we have 2 cubes, number 2 and number 7, which are sliced by both the XY and the XZ plane. So that first slice gives you your triangular prism, but then your second slice, what happens then is it creates a square-based pyramid. And now the pyramid still has length and width of 1/2, so the volume of that pyramid would be equal to 1/3 the volume of that original cube, which was 1/8, which gives us 1/24. Now we have 2 of these, so let's multiply that by 2, which gives us 2/24, which is the same as 1/12. So now if we add up all these areas, 1/4 plus 1/4 plus 1/12, we get a total volume of 7/12. So our answer is B.